Well, welcome to general chemistry. We're going to go just jump right in to our first chapter. Again, I mentioned this in the welcome video, but I'm going to be kind of following the chapters and parts that you find in the textbook, the OpenStax textbook. So you'll see this like here on this title page that we're going to be going through sections 1.1 to 1.3. And so let's just kind of dive in. This is a chemistry course, and whether you've had high school chemistry or not, or maybe this is your first experience with chemistry, it's important to know simply like, what is this? What are you going to be studying for the next academic year? And simply, the chemistry is just the study of the properties and behavior of matter. In my opinion, chemistry is cool. I know that makes me sound like a nerd, but just kind of, give me a little leeway here. Chemistry governs so much more than just being something you got to take, to fulfill a requirement. Chemistry is the central science of pretty much all others. You will need chemistry in order to explain biological processes. In fact, if you are going to take organic chemistry, or biochemistry later, you will see that it's chemistry itself that governs everything, governs your biological processes. It governs the synthesis of materials. It governs things like with purifying crude oil and the way your cell phone works and your computer works. All of that can be traced back to chemistry. And you experience chemistry every day, every second, literally, whether you know it or not. There's you can see some examples here: digesting food, synthesizing polymers for clothing, cookware, credit cards, even expanding that to like cosmetics, perfumes, colognes. You can't get away from chemistry. And so as we go through this course, you're going to look and discover the different examples of changes in the composition and structure of matter, how we classify them, how we can predict behavior of chemicals and predict chemistry behavior, as well as the changes in energy that accompany these. Now, like the study of any science, chemistry is founded on the scientific method. If you've taken any sort of science course, this is usually one of the first things that is always taught, because chemistry is based on observation and experimentation. You can't just say, I think this happens the way it happens, and that's that. You have to test it. And you don't just test it once, you test it over and over, and then other people test it, and then they make changes, and then they, revise, and then it's just this kind of circular process. And does the routes to obtain scientific knowledge might be different, but most of them are common in one certain aspect, is that a hypothesis is formed first. Hypothesis is a tentative explanation of observations. So you observe something happen, and then you come up with an explanation for why you think that happened. And a hypothesis does not have to be correct at the very beginning. In fact, many hypotheses change once experimentation is done, and then that hypothesis is revised. And so there's this constant circular process here from hypothesis to experimentation. And then did something work? No. Okay, so let's revise our hypothesis. Or an experiment proved some other aspect that we weren't even thinking about. And all of this experimentation contributes to a larger body of knowledge. And eventually, with a lot of additional testing that supports your hypothesis, that hypothesis becomes a theory. And we use these theories to kind of explain why a scientific law happens. And so at face value, kind of was like, what's the difference? You know, the law and theory kind of look the same. A law is basically just stating that something happens over and over again, like the law of gravity. Okay. If you throw something up in the air on planet Earth, it comes falling to the ground. That's the law of gravity. That doesn't explain why that happens. And that's where theories come in. Theories are acquired after much experiments, much testing that all supports itself. You have a very large body of support for that theory. Now, when we study chemistry, we look at three main domains of chemistry. The first of these is what we call macroscopic. These are things that we can sense directly by human sight and touch. So a lot of what you will be doing in chemistry lab will be macroscopic observations. Mix a couple things together and we observe what happens. The second is microscopic. Now, this is a domain that's often visited by the imagination. Now, I don't want you to think that this is like, oh, abstract and like, oh, let's just think of something and then that's reality. No, these are backed up with experimentation, but think about, for example, what makes up an atom. I'll talk about more of this in another chapter. But atoms are made up of what we call subatomic particles, called like neutrons, protons, and electrons. We don't see those things. We can't even see those things with powerful microscopes. We can see evidence of them, and that's where our knowledge of their existence comes into being. But we have to think about them in our imagination. Um, Sometimes we can observe microscopic with advanced instrumentation. Like, for example, a microscope. Or something even more powerful like an electron microscope, or super powerful like they call it a scanning tunneling microscope, and that allows us to kind of see things that are not visible to our human sight. And then the third domain is more, how do we report these things? So this is called the symbolic domain. This is a specialized language which you will learn a little bit about in this course. It's a specialized language used to represent components of the previous two domains, of the macro and microscopic domain. Now, just to kind of show you an example of all three of these, let's take a look at this picture. This picture illustrates all three of these domains. So the picture itself, let's say you're on a boat and you're observing this. All of this here is under the macroscopic domain. That's what you can observe. You can feel the water. You can feel the ice on the glacier. You can see all of those things. You can see the clouds in the sky. But what you can't see are how the molecules of water are associating with each other in the various observations of the macroscopic domain. Like you can't see in water vapor how the molecules are far apart. You can't see in solid ice that the molecules are close together and very rigid and not moving around. You can't see in liquid water the molecules of water just floating around and associating with each other in that way. So that's an example of the microscopic domain. And then this symbology right here, represents the symbolic domain. Like we use the word water, but what really is that? How do we describe, what makes up water? Well, we use formulas like H2O. Water is made up of two hydrogen atoms and one oxygen atom. Well, what other symbology do we use? Well, we use these kind of symbols here like G and S and L for solid, liquid, and gas states of matter. So we will be kind of like, or sort of learning a new language on how we report on the micro and macroscopic domains. Now, since chemistry is the study of matter, um, what is matter anyways? Matter is anything that occupies space and has mass. And over the course of this semester, we're going to highlight three very common states of matter: solid, liquid, and gas. Now, it's not enough just to kind of know those three things. Let's talk a little bit about the kind of generic properties of each of those three states of matter. Solids are rigid and have a definite shape. Okay, kind of using the water again, like ice. Ice is solid water and it has a definite shape to it. If we're going to kind of go a little bit more in the microscopic, if we were able to look at the molecules of water or atoms that are in a solid, if we could observe them, we would see that this type of matter vibrates in place. The molecules do not move around. Like if you take a solid and you kind of like shake it up in a bottle, the molecules don't move around at all. They don't change their shape because they hit the wall of the glass or anything like that. So the atoms or molecules in a solid stay in place and are rigid. A liquid will take the shape of whatever container it's put into. We call that a fixed volume. But a liquid does not have a definite shape. I'll use liquid water as an example. So you have a glass of water. That water will take the shape of its container. As soon as you pour that water out, it does not stay as a cylinder. It spreads itself all over, all over the floor. And if we look at, again, kind of the microscopic arena of a liquid, the molecules of a liquid are close together, but move around. Now I'm going to kind of go back to this picture here to look at the difference between solid water and liquid water. In solid here, these molecules of water are stuck together. They won't move around. But in liquid water, these molecules are bumping into each other. They're moving around all over the place. Now for gases have no fixed shape or volume. And in fact, gases will expand to fill their container. And if we were to look microscopically, particles or the molecules of a gas are widely separated. So again, using the water here as an example, you can see that in water in the gas phase, the molecules are very far apart and they're moving constantly. They're not in a fixed spot. So in this graphic here kind of demonstrates again the kind of the properties of each state of matter, with solids having a fixed shape and volume. Liquids will take the shape of their container and they have a fixed volume. One thing to note is that liquids, they will tend to form this horizontal surface. Sometimes, if the cylinder or the container it's in is thin enough, so let's say like a graduated cylinder. So if there's a liquid in there, it tends to have this kind of curved um, um, surface to it. We'll go over that in lab. And then gases will expand to fill their container. Now, just very briefly, I want to acknowledge that there is a fourth state of matter. We're not going to talk anything more about it outside of this particular slide, but there is a state of matter known as plasma. And this is a gaseous state of matter that has been superheated, causing an ionized gas. So that's pretty much all I want to say about plasma. We're not going to go any more in depth to it, but if you're doing a Google search like what are the states of matter, that's usually one that comes up, and it's not nearly as common as solid, liquid, or gas. And as I said, we probably will not highlight it again in this course. Now, finally, in this lecture, one of the things I want to talk about is how we quantify matter. One of the most common things that we do is we look at the mass of matter. Mass is simply the measure of matter in an object. Now, how does this differ from the weight of an object? The weight is the effect of gravity on an object. You say, well, aren't those two the same? Can't I put, some table salt on a balance and know how much it weighs? And that's also its mass. Yeah, on Earth, mass and weight can be the same value. But where they start to differ is if there is a different effect of gravity. So if you're an astronaut and you were to go up to the moon, the amount of matter that makes you up does not change. You don't suddenly lose a whole bunch of matter. But if you were to weigh yourself on the moon, you would weigh a lot less because the effect of gravity is a lot less on the moon. And so mass and weight would be different values on the moon. But kind of for all intents and purposes, on Earth, mass and weight will typically have the same value. But it's not correct to say that mass and weight have the same definition. So that's where we're going to stop with this lecture. I would definitely take some time, review it, and then head on to the next.